Tonight, we're going to talk about Proxima Centauri, the star closest to our own sun. You've probably heard that it's our nearest neighbor among the stars, 4.24 light-years away. That sounds close, right? Close enough that reaching it feels like a matter of time, not a matter of possibility. But here's what's going to change that. The distance on paper was never the real problem. The real problem shows up the moment you try to actually cross it, when propulsion that doesn't exist yet, radiation with no precedent, and a timeline stretching past a single lifetime all show up at once. By the end of tonight, you're going to understand exactly why that distance is so much harder to close than it sounds, and why the nearest star in the universe might still be permanently out of our reach. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Let's start with the number itself. A light year is the distance light travels in one full year. Light moves at about 186,000 miles every second. Multiply that speed by the seconds in a year, and you get roughly 5.9 trillion miles. 1 light year. Now, multiply that by 4.24. The distance to Proxima Centauri comes out to about 25 trillion miles. 25 trillion. Try to picture that number honestly, and you'll find you can't. Nobody can. So let's ground it a little. The farthest any human being has ever physically traveled is the Moon, about 240,000 miles away. We covered that distance in 3 days. Now compare that trip to the trip to Proxima Centauri. 25 trillion miles is about 104 million times farther than the Moon. If the 3-day trip to the Moon was scaled up proportionally, the equivalent journey to Proxima Centauri would take roughly 850,000 years at the exact same speed. 850,000 years, just to arrive, using nothing faster than what carried astronauts to the Moon in 1969. Proxima Centauri is not slightly farther than anything we've ever reached. It's not 10 times farther, or 100 times farther. It's on a completely different scale of distance. Our entire history of space travel starts to look like a person taking one step outside their front door and calling it a journey around the world. Now, consider our fastest machines, because this is where the story starts to get uncomfortable. Voyager 1, launched in 1977. It's the farthest human-made object ever to leave the solar system, moving outward faster than anything else we've ever sent in that direction. It's currently moving at about 38,000 miles per hour relative to the Sun. That's an extraordinary speed by any human standard. It could cross the continental United States in about 4 minutes. And yet, at that speed, if Voyager 1 was somehow aimed directly at Proxima Centauri, the trip would take about 75,000 years. 75,000 years on our best outbound spacecraft to reach our closest neighboring star. We've been launching spacecraft for less than 70 years. In that time, our top speed has climbed dramatically, from nothing at all to tens of thousands of miles per hour. And it still isn't within reach of what a real interstellar trip would demand. So why not just build something faster? That's always the next question. And it's a fair one. The problem is the speed of light itself. It isn't just a record we haven't broken yet. It's a wall built into the structure of the universe. Nothing with mass can reach the speed of light, let alone exceed it. As an object made of matter approaches that speed, the energy required to keep accelerating, it climbs toward infinity. Get close enough to light speed, and you would need an infinite amount of energy to go even a fraction faster. That's not a limitation of current engineering. That's a limitation written into the physics of space and time themselves. Einstein's special relativity described it over a century ago. Every particle accelerator and every astronomical observation since has confirmed it. Even if we could somehow build an engine of perfect efficiency, one that converted matter directly into thrust with no waste at all, we would still be bound by that ceiling. We could get close to light speed. We could never touch it, and we could never cross it. So, let's be generous and imagine a spacecraft that reaches 10% of the speed of light. Something far beyond anything we've built, but at least, theoretically, within the reach of known physics. At 10% of light speed, roughly 67 million miles per hour, the trip to Proxima Centauri would take about 42 years. 42 years is almost believable. It's within a human lifetime. A crew could leave as young adults and arrive as older adults, still capable of stepping onto a new world. That single number, 42 years at 10% light speed, is the number that keeps interstellar travel from being pure fantasy. The trouble is getting anything to 10% of light speed in the first place, and slowing it back down again once it arrives. Chemical rockets are nowhere close to sufficient. These are the same rockets that took humans to the moon and still launch every satellite in orbit today. The fastest chemical rocket exhaust velocities top out around 3 miles per second. To reach even 1% of the speed of light using a chemical rocket, you would need a mass ratio so extreme that the fuel alone would outweigh anything achievable with known engineering by many orders of magnitude. You simply cannot chemically combust your way to interstellar speeds. The energy density of chemical fuel is millions of times too low. This is why every serious proposal for interstellar travel abandons chemical propulsion within the first few pages. Nuclear propulsion does better. In the 1950s and 60s, a group of physicists worked on a concept called Project Orion. It was a spacecraft that would propel itself by detonating small nuclear bombs behind it, riding the shockwaves forward like a surfer on repeated waves. On paper, Orion could theoretically reach speeds of around 3 to 10% of light speed. That would put Proxima Centauri within reach in 50 to 140 years. But Orion comes with the obvious problem of releasing enormous amounts of radioactive fallout, both at launch from Earth and, depending on design, potentially throughout the journey. The 1963 Partial Test Ban Treaty effectively ended any real-world testing of nuclear detonation propulsion. The political and environmental obstacles to ever reviving it remain immense. Fusion propulsion is the next step up. It's the concept behind Project Daedalus, a 1970s study by the British Interplanetary Society. It designed a theoretical, unmanned probe powered by fusion pulse engines capable of reaching about 12% of light speed. At that speed, Daedalus could reach Barnard's star, about 6 light-years away, in around 50 years. The catch is that fusion propulsion at that scale requires fuel, specifically helium-3, in quantities we cannot currently produce or mine anywhere on Earth in sufficient volume. Some proposals suggest mining it from the atmosphere of Jupiter or Saturn. That introduces an entirely separate set of engineering problems that remain unsolved. Then there's antimatter. In principle, it's the most efficient fuel physics allows. When matter and antimatter meet, they annihilate completely. They convert 100% of their mass into energy, following the relationship E equals mc squared. No chemical or nuclear reaction comes close to that efficiency. A spacecraft, powered by matter-antimatter annihilation, could theoretically reach a significant fraction of light speed with a manageable amount of fuel. The problem is that we have only ever produced antimatter in quantities measured in nanograms, at staggering cost, inside particle accelerators. Producing and then safely storing enough antimatter to power an interstellar mission is not simply difficult. You'd need containment fields strong enough to keep it from touching any normal matter and annihilating instantly. With current technology, it's essentially impossible. We are talking about a fuel source more efficient than anything else we know of. It's also more inaccessible than anything else we know how to make. There's one more idea that has actual momentum behind it right now, and it takes a completely different approach. Instead of carrying fuel, you leave the fuel at home. That's the concept behind Breakthrough Starshot, an initiative announced in 2016, backed by funding from Yuri Milner and endorsed by physicists, including the late Stephen Hawking. The idea is to build thousands of postage stamp-sized spacecraft, each attached to an ultra-thin light sail, only a few meters across. You push them to relativistic speed using a massive array of ground-based lasers, firing for just a few minutes at launch. Because the spacecraft themselves would weigh only a few grams, that brief laser push could theoretically accelerate them to 20% of the speed of light, enough to reach the Alpha Centauri system in about 20 years. It's a genuinely elegant idea. It's the closest thing we have to a realistic path toward interstellar distances within the next century. But it comes with serious limitations. There's no way to slow these tiny probes down once they arrive. They would streak through the Alpha Centauri system at 20% of light speed and be gone again in a matter of hours. They'd capture what images and data they can during that brief flyby, before continuing on into deep space forever. There's also the problem of building a laser array powerful enough to do the pushing. It would require gigawatts of sustained power and phased coordination across a huge ground-based array, technology that doesn't yet exist at the scale required. And the tiny probes themselves would need to survive collisions with interstellar dust at relativistic speed. That brings us to a problem that almost never gets discussed, and it might be the most dangerous one of all. Interstellar space is not empty. It only looks empty. Scattered through the vast gap between stars are grains of dust, individual atoms of hydrogen and helium, and occasionally larger particles. All of it is left over from exploded stars and the slow churn of galactic formation. The density is incredibly low, maybe 1 atom per cubic centimeter on average. That's far emptier than the best vacuum we can create in a laboratory on Earth. Under normal circumstances, this near vacuum is harmless. You could sit in it indefinitely and never notice a single collision. But speed changes everything. At 10 or 20% of the speed of light, even a single grain of dust becomes a serious threat. Kinetic energy scales with the square of velocity. A particle moving at that speed carries an amount of destructive force wildly out of proportion to its tiny size. A dust grain, weighing a fraction of a gram, striking a spacecraft at 20% of light speed, could deliver an impact equivalent to a small explosive charge. Now, imagine a spacecraft traveling for decades through that same interstellar medium. It's not a question of whether it gets hit. It's a question of how many times and how catastrophic the hits turn out to be. Any real interstellar spacecraft would need shielding designed specifically for this problem, likely in the form of a sacrificial layer positioned ahead of the main hull, something built to vaporize on impact and disperse the energy of a strike before it reaches anything critical. Designs for Project Daedalus included a beryllium shield, roughly a millimeter thick for exactly this reason. They also included a secondary cloud of dust released ahead of the craft to pre-vaporize incoming particles before they made contact with the hull itself. Even with shielding like that, the risk never fully disappears. Every additional year in transit is another year of exposure. It's another set of dice rolled against the possibility of a strike large enough to end the mission entirely. The longer the journey, the more the odds stack against you. And journeys to Proxima Centauri, at any speed we can currently imagine, are long. Now consider time itself, because at the speeds required for interstellar travel, time stops behaving the way it does here on Earth. This is one of the strangest and most misunderstood consequences of relativity, and it applies directly to any real mission toward Proxima Centauri. As an object's speed increases and approaches the speed of light, time for that object begins to slow down, measured relative to a stationary observer. This isn't a trick of perception. It's a measurable, physically real effect. Atomic clocks flown on aircraft and satellites have confirmed it repeatedly. GPS satellites confirm it daily, since they must correct for this exact effect to remain accurate. At 10% of the speed of light, the time dilation effect is small but real, on the order of 0.5%. At 50% of light speed, it becomes significant, close to 15%. At 90% of light speed, a crew could experience less than half the time that passes for the people they left behind on Earth. Push that further, to 99% of light speed, and the ratio becomes extreme. A crew might experience a journey lasting a handful of years, while decades, or even centuries, pass back on Earth. This creates something science fiction has long been fascinated by, and reality would force any interstellar crew to actually confront. A round trip to Proxima Centauri at extreme relativistic speed might feel, to the crew, like a matter of years. But by the time they returned, Earth could have moved forward by generations. Everyone they knew would be gone. The culture, the language, the technology, even the political boundaries of the world they left could be unrecognizable. They would step off their spacecraft into a future that had left them behind, strangers on the very planet they were born on. This is sometimes called the twin paradox. It's most famously illustrated by imagining one twin staying on Earth while the other travels near light speed and returns younger than their sibling. It isn't a paradox in the sense of a contradiction. It's simply how time works when velocities get close enough to the speed of light. Any crew attempting true relativistic interstellar travel isn't just leaving their planet behind. They're leaving their entire timeline behind, trading their future for a one-way trip into someone else's. Then there's radiation, a hazard that barely gets mentioned in most popular discussions of interstellar travel. Mission designers consider it absolutely critical. Once you leave the protection of Earth's magnetic field and the Sun's heliosphere, you're exposed to galactic cosmic rays. These are high-energy particles accelerated by distant supernovae and other violent cosmic events, traveling through space at close to the speed of light. On Earth, our atmosphere and magnetic field absorb almost all of this radiation before it reaches the surface. Astronauts on the International Space Station, still within Earth's protective magnetosphere, absorb significantly more radiation than people on the ground. Astronauts who traveled to the Moon, briefly outside that protection, experienced measurably higher radiation exposure during those few days than anyone on a mission confined to low Earth orbit. Now, stretch that exposure out across decades of interstellar transit fully outside any planetary or solar protection, and the numbers become genuinely dangerous. Sustained exposure to galactic cosmic rays over a multi-year or multi-decade journey would significantly increase the risk of cancer, damage to the central nervous system, and cumulative harm to nearly every organ system in the body. Shielding helps. But shielding against high-energy cosmic rays is far harder than shielding against the kind of radiation solar flares produce. The particles involved carry so much more energy that they can pass straight through many conventional shielding materials, sometimes producing secondary radiation as they do. Effective shielding would likely require thick layers of water or hydrogen-rich plastic. More ambitious designs would need actively generated magnetic fields around the spacecraft itself, mimicking in miniature the protection Earth's own magnetosphere provides. Every one of these solutions adds mass, and mass is the one thing an interstellar spacecraft can least afford. More mass means more fuel, and more fuel means more mass to accelerate. It's a spiral that makes every gram matter enormously. Given all of this, many serious thinkers have concluded that the only realistic way to send humans to Proxima Centauri, using propulsion within reach of foreseeable technology, isn't a fast, relativistic sprint at all. It's a slow, patient crawl spread across many human generations. This is the generation ship concept. A self-contained vessel large enough to support a stable population, traveling at only a small fraction of the speed of light, taking centuries rather than decades to complete the journey. The people who arrive at Proxima Centauri would be the great-great-grandchildren, many times removed, of the people who first stepped aboard. Nobody who launches would ever see the destination. Nobody who arrives would have ever seen Earth. The engineering challenge here isn't really propulsion anymore. It's sustainability. A generation ship would need to function as a fully closed ecological system for centuries without fail. It would need to recycle every drop of water, every breath of oxygen, every scrap of food, with no possibility of resupply from Earth, and no possibility of correcting a catastrophic failure from outside. Even small experiments in closed ecological systems here on Earth, like the Biosphere 2 project in the early 1990s, revealed just how difficult this actually is. Oxygen levels dropped unexpectedly. Crop yields failed to match projections. Unplanned chemical reactions between the concrete structure and the atmosphere consumed oxygen faster than anticipated. And that experiment lasted only about 2 years, inside a structure sitting safely on the surface of the Earth, with scientists on the outside able to intervene if something went catastrophically wrong. A generation ship would need to solve every one of those problems, and countless others, for centuries. In the vacuum of interstellar space, with absolutely no outside help available at any point. Then there's the human side of the problem, which may be even harder than the ecological one. A closed population, traveling for many generations, faces a genetics problem. A small founding population risks inbreeding and a dangerous loss of genetic diversity over time. The crew would need to be large enough, likely numbering in the many hundreds or low thousands, to maintain a healthy gene pool across generation after generation. It faces a social and political problem too. Maintaining stable governance, shared purpose, and social cohesion across centuries is something human societies have essentially never had to do in an enclosed, inescapable space with no ability to leave. And that's spanning dozens of generations who never chose to be born into this mission in the first place. And it faces a psychological problem. Every generation born aboard the ship would live and go without ever setting foot on solid ground, without ever seeing an open sky, without ever experiencing the planet their ancestors called home. They'd exist entirely inside a metal vessel, drifting through darkness because of a decision made by people who were gone long before they were born. Even if a generation ship succeeded, even if a healthy, well-governed, ecologically stable population arrived safely at the Alpha Centauri system some 4 to 6 centuries after departure, they would still face a final layer of isolation that never goes away. Communication. Radio signals, like all electromagnetic radiation, travel at the speed of light. That's the same absolute speed limit that governs everything else in this story. A message sent from that new colony back to Earth would take 4.24 years to arrive. A reply would take another 4.24 years to travel back. Every single exchange, no matter how simple, would carry a minimum round-trip delay of 8.5 years. Think about what that actually means for communication. There is no conversation possible across that gap, not in any sense we'd recognize. You could not ask a question and receive an answer within your lifetime's worth of ordinary patience. A child born the year a message was sent would be entering adolescence by the time a reply arrived. Any colony at Proxima Centauri would, by necessity, become functionally independent almost immediately. It would make every decision on its own, solve every crisis on its own, and develop its own culture and history, largely disconnected from whatever Earth became in the centuries since departure. The idea of a unified human civilization spanning multiple star systems, staying in close contact, and sharing news and culture and politics in anything resembling real time simply isn't physically possible across interstellar distances. Every colony beyond our solar system would effectively become its own separate branch of humanity, cut off not by choice, but by the unbending physics of light and time. Here's a detail that makes the whole problem even worse, one that almost never comes up in casual conversation about interstellar travel. Proxima Centauri is not sitting still, waiting patiently for us to arrive. Nothing in the galaxy sits still. Every star, including our own sun, is in constant motion, orbiting the center of the Milky Way at tremendous speed. It's also drifting relative to its neighboring stars due to countless small gravitational influences accumulated over billions of years. Proxima Centauri has its own motion through space, distinct from our sun's motion. The two are not moving in identical directions. Right now, Proxima Centauri is actually drifting closer to us, not farther away, due to its orbital path relative to the Sun. In roughly 26,000 years, it will reach its closest approach, coming within about 3.1 light-years of our solar system. Then it'll begin drifting away again as it continues along its own orbit around the galactic center. This matters enormously for mission planning. A spacecraft launched today cannot simply aim at where Proxima Centauri currently sits in the sky. Given a journey lasting decades or centuries, the star will have moved substantially by the time the spacecraft arrives. Navigators would need to calculate a trajectory aimed not at where Proxima Centauri is right now, but at where it will be after however many decades the crossing takes. They'd need to account for its motion relative to our own sun, correcting continuously throughout the voyage as tracking data refines the prediction. A small error early in that calculation, left uncorrected, could compound over a journey of light years into a miss of trillions of miles. You'd arrive at the right distance from home, but find empty space where the star system was supposed to be. Step back and look at what actually surrounds us, because Proxima Centauri isn't an isolated case. It's simply the closest example of a pattern that repeats endlessly the farther out you look. Within about 10 light-years of the Sun, there are only around a dozen known stars, most of them faint red dwarfs, invisible without a telescope. Barnard's star sits at 6 light-years. Sirius, the brightest star in our night sky, sits at 8.6 light-years, more than twice as far as Proxima. Epsilon Eridani sits at about 10.5 light-years. Tau Ceti at about 12 light-years. If Proxima Centauri, at 4.24 light-years, still requires decades of relativistic travel or centuries of generational travel just to be reached at all, using every propulsion concept physics currently allows us to seriously consider, then every other star in that list is proportionally worse. Sirius isn't twice as far in some abstract sense. It's twice the travel time, twice the radiation exposure, twice the dust collision risk, twice the structural and social and psychological endurance required of any crew attempting the crossing. And Sirius is one of our closer neighbors. The galaxy contains somewhere between 100 billion and 400 billion stars. The overwhelming majority of them thousands or tens of thousands of light-years distant. If the nearest star demands multiple human lifetimes and technology we don't yet possess, and it's the one single star that should represent the easiest possible interstellar destination, then the rest of the galaxy isn't simply farther away. It's functionally unreachable, not for lack of ambition, but because of what distance itself actually costs. Let's talk more carefully about what's actually waiting at the end of this journey, because that matters too. Proxima Centauri is not one star, but part of a larger system. It's gravitationally bound to 2 other stars, Alpha Centauri A and Alpha Centauri B, which orbit each other at a separation ranging between about 11 and 36 astronomical units. They complete one orbit roughly every 80 years. Proxima itself is a small, dim red dwarf, orbiting that central pair at an enormous distance. It's so far out that it takes Proxima roughly 550,000 years to complete a single orbit around them. Proxima Centauri is small, only about 12% the mass of our Sun. It produces only a small fraction of our Sun's light and heat. If you stood on a planet at a comfortable temperature around Proxima Centauri, you would need to orbit so close to the star that you'd almost certainly become tidally locked. One side of your world would face the star permanently, while the other side remained locked in permanent darkness and cold. That arrangement creates brutal weather patterns, permanent temperature, extremes between the day side and night side would drive powerful, possibly world-scouring winds along the border between light and dark. Red dwarfs, like Proxima, also tend to be far more volatile than they first appear. Despite their small size and dim light, they frequently produce enormous stellar flares. These are sudden bursts of radiation, many times more powerful, relative to the star's size, than anything our own Sun produces. In 2017, astronomers observed Proxima Centauri unleash a flare so powerful it briefly brightened the star by a factor of many multiples of its normal luminosity. An event like that would have stripped away a significant portion of atmosphere from any nearby, unprotected planet. In 2016, astronomers confirmed the existence of a planet orbiting within Proxima's habitable zone, called Proxima Centauri b. It's roughly Earth-sized and positioned at a distance where liquid water could theoretically exist. It's a tantalizing discovery, the closest known potentially habitable world beyond our solar system. But given how frequently and violently Proxima flares, many researchers now suspect that any atmosphere the planet once had may have been stripped away entirely, leaving a bare, irradiated rock rather than anything resembling a second Earth. In other words, there's a real possibility that the destination itself turns out to be uninhabitable. Even after solving every problem of propulsion, radiation shielding, generational sustainability, and precise navigation across a moving target, we might still find a rocky world with no breathable air and no meaningful shelter. A world orbiting a star that behaves more like a temperamental furnace than a steady source of light. Now, consider the maintenance problem, something engineers who study long-duration spaceflight worry about constantly, and the public almost never hears about. Every piece of equipment humans have ever built eventually fails. Metal fatigues. Seals degrade. Electronics succumb to radiation damage over time, their delicate circuitry slowly corrupted by the same cosmic rays that threaten the crew. On the International Space Station, equipment failures happen regularly and require ongoing repair, replacement, and improvisation. That's a spacecraft in low Earth orbit, constantly resupplied, constantly monitored from the ground, staffed by rotating crews of highly trained specialists. Now imagine that same station, or something built along similar engineering principles, sealed off completely. No possibility of resupply. No ground control. No replacement parts beyond whatever was carried at launch. And a journey lasting not months, but decades or centuries. Every system aboard a generation ship or a fast relativistic craft would need total reliability across time frames far beyond anything ever engineered before. Or it would need the ability to be manufactured and repaired entirely on board, using only materials carried from Earth or mined along the way. That likely means bringing along industrial-scale manufacturing capability and raw material stockpiles. It also means generations of skilled engineers trained to maintain systems using knowledge passed down like an oral tradition, because there's no guarantee the original engineering documentation survives fully intact and comprehensible across 2 or 3 or 10 human generations, however carefully preserved. Consider how much has changed in engineering knowledge and terminology over just the last 100 years. Now, imagine trying to preserve perfect technical continuity across 3 or 4 centuries, with the only consequence of failure being the permanent loss of the ship's ability to sustain its own crew. Every redundant system eventually becomes a single point of failure once its spare parts run out. Every skill eventually needs to be relearned, or it's lost. A generation ship isn't just a vehicle. It has to be a self-sustaining, self-repairing, self-educating civilization in miniature, one that cannot afford to forget anything important for as long as the journey lasts. There's also a deceleration problem that gets overlooked constantly. Most discussions of interstellar travel focus entirely on how to get up to speed, and almost never on how to slow back down. Accelerating to a meaningful fraction of the speed of light is only half the challenge. Once a spacecraft is moving at 10 or 20% of light speed, it can't simply coast into orbit around its destination star. It has to decelerate, using roughly the same amount of energy required to accelerate in the first place. Any realistic mission profile needs to budget for 2 enormous propulsion events instead of 1, doubling the fuel or energy requirements right from the start. This is precisely why concepts like Breakthrough Starshot, which rely on a one-time laser push from Earth, can only ever manage a flyby. There's no laser array waiting at Proxima Centauri to catch an incoming probe and slow it down. Any deceleration has to be carried entirely aboard the spacecraft itself. That means carrying propellant, or relying on some form of drag from the interstellar medium, or using the destination star's own light pressure and gravity in an extremely precise braking maneuver planned years in advance, with no opportunity to correct a mistake once the maneuver begins. A single error in timing or trajectory during deceleration wouldn't just delay the mission. It would send the spacecraft hurtling past its target at extreme speed, out into the darkness beyond, with no way to turn around and no fuel left to try again. For any mission that actually intends to stop, to orbit, to land, to build something at Proxima Centauri, rather than simply fly past and glimpse it for a few hours, deceleration might be a harder engineering problem than the outbound journey itself. All of this raises an uncomfortable question, one that physicist Enrico Fermi is often credited with first articulating in a slightly different form back in 1950. If interstellar travel is this difficult, even across the shortest possible distance in our galaxy, what does that imply about the rest of the universe? The Fermi paradox asks why we haven't detected any clear evidence of other intelligent civilizations. Given the sheer number of stars and the vast age of the galaxy, despite billions of years during which such civilizations could theoretically have expanded outward. One of the proposed explanations is disarmingly simple. Maybe interstellar travel really is this hard everywhere, for everyone, always. Maybe the distances between stars function as a kind of natural quarantine. Civilizations stay isolated within their own solar systems, not because of any lack of intelligence or ambition, but because the physics of the universe itself makes crossing those gaps extraordinarily costly, regardless of how advanced a civilization becomes. Proxima Centauri is the nearest possible target anywhere in the universe. If it already demands multiple human lifetimes of travel time, even under the most optimistic, realistic mission designs, then the silence we observe when we search the sky for other civilizations might not indicate that intelligent life is rare. It might simply indicate that intelligent life, wherever it exists, tends to stay close to home for exactly the reasons this entire discussion has laid out. Vast distances, punishing radiation, the impossibility of real-time communication, the sheer scale of engineering and social cohesion required to survive centuries of enclosed transit. If even the shortest hop between two stars is this brutal, it becomes a lot easier to understand why the galaxy might be full of life that never leaves home. Each civilization sitting quietly around its own star, separated from every other by gulfs too wide to cross. Set the physics aside for a moment and look at the economics, because cost turns out to be its own kind of distance. Every serious study of interstellar propulsion runs into the same wall. The energy required to accelerate even a modest payload to a meaningful fraction of light speed is staggering. Accelerating a spacecraft with a mass of just 1 metric ton to 10% of the speed of light requires roughly the same amount of energy the entire world currently consumes in a single day. Scale that up to a spacecraft large enough to carry a crew, along with life support, shielding, and supplies, and the energy requirement grows into numbers that dwarf anything humanity has ever generated or stored in one place. Breakthrough Starshot, the most realistic near-term proposal, estimated its total cost somewhere in the range of $5 to $10 billion. That included development of the laser array and the fleet of tiny probes for a mission sending gram-scale probes on a one-way flyby with no deceleration and no crew. Scale that concept up to something capable of actually stopping at Proxima Centauri. let alone carrying and sustaining human passengers across centuries. And the cost estimates move into territory that no single nation currently possesses the economic capacity to fund. Arguably, no coalition of nations does either. Some analyses have suggested that a full-scale generation ship, built with technology only modestly beyond what we currently possess, could require a global economic commitment sustained across many decades. That would mean redirecting a meaningful fraction of the entire world's industrial output toward a single project with no return on investment for centuries, if ever. That's not a technical problem. It's a question of whether any civilization would ever choose to make that sacrifice. It's a question of whether it could remain politically and economically committed to a project on a timescale longer than most civilizations in human history have even existed. Let's imagine for a moment what daily life would actually look like for someone aboard a generation ship centuries into a journey to Proxima Centauri, simply to make this less abstract. This person was born aboard the vessel. They will go without ever having felt open air on their skin, without ever having seen a horizon that wasn't curved by the hull of their own ship. They'll never experience weather, rain, an ocean, or an unfiltered sky full of stars that weren't simply the view through a viewport. Their entire understanding of Earth would come from records, photographs, videos, and stories passed down from ancestors who themselves may have only heard about it secondhand. Their work would likely be tightly structured around the ship's survival, agriculture, engineering maintenance, education of the next generation. A closed system this fragile cannot afford idle hands or unproductive time across multiple lifetimes. Their social world would be permanently, unchangeably small. It would be limited to whatever population the ship was designed to carry, with no possibility of meeting anyone outside that group, ever, for their entire life. Concepts we take completely for granted, choosing a new city to live in, traveling somewhere unfamiliar, meeting a stranger from a different culture, simply wouldn't exist for them. Every person they will ever know for their entire life, they were essentially born already knowing. Psychologists who study isolation consistently find that even much shorter periods of confinement and limited social contact produce measurable psychological strain, conflict, and in some cases, serious mental health decline. This research draws on Antarctic research stations, submarine crews, and long-duration spaceflight simulations. The longest isolation experiments we've ever run only lasted a year or two. A generation ship would need to solve these same challenges continuously, for centuries, across populations who never consented to the mission in the first place because they were simply born into it. None of this means the effort is pointless. There's a difference between something being extraordinarily hard and something being impossible. Serious research into interstellar propulsion continues today, in forms far more advanced than the paper studies of the 1970s. NASA's innovative Advanced Concepts program has funded early-stage research into concepts ranging from advanced fusion drives to laser-propelled sails, evaluating which ideas might eventually mature into real hardware. Private organizations continue refining the breakthrough Starshot concept, working through the engineering of ultra-lightweight sails and high-power laser arrays. The tiny onboard electronics would need to survive both launch acceleration and decades of raw exposure to interstellar radiation. Advances in materials science continue incrementally, year after year, even without a single dramatic breakthrough. Researchers are working on sails that are simultaneously reflective, incredibly thin, and resistant to degradation from radiation and micrometeorite impacts. This entire field of study is also still remarkably young. Humanity's first artificial satellite, Sputnik, launched in 1957. The first human being reached orbit in 1961. We landed on the moon just 8 years after that, using computers with less processing power than a modern kitchen appliance. In less than 70 years, we went from having no spaceflight capability at all to operating robotic probes on Mars, telescopes that can detect the atmospheres of planets orbiting other stars, and a continuously crewed research station orbiting the Earth. None of that means interstellar travel is imminent, and nothing in this discussion should be read as suggesting otherwise. But it's a reminder that predicting the ceiling of future technology from where we stand today has historically been a losing bet. The engineers of the 1960s would have found many things about our current spaceflight capability entirely unremarkable, and many other things almost unimaginable. We genuinely don't know which category interstellar propulsion will eventually fall into a century or two from now. But here's the honest, grounded version of where things actually stand today, without exaggeration in either direction. Every propulsion concept currently within reach of known physics and foreseeable engineering points toward a journey to Proxima Centauri, lasting somewhere between several decades and several centuries. It depends entirely on how much energy a future civilization is able and willing to commit to the attempt. Every version of that journey carries serious, unsolved problems in radiation shielding, micrometeorite protection, and closed system sustainability. For anything involving a living crew, there are also genuine questions about whether humans can maintain functional societies across multi-generational confinement. And even in the most optimistic version of events, where every engineering problem gets solved, the destination itself might turn out to be a radiation-blasted rock orbiting a temperamental red dwarf, rather than anything resembling a second home for humanity. None of this is a reason for despair. It's simply the honest shape of the problem. The nearest star in the universe, the single closest destination that could ever exist beyond our own solar system, is not a short hop away. It is not something a determined civilization could reach within a few decades using an ambitious but modest engineering push. The way we reached the moon in the 1960s. It is a multi-generational undertaking. It requires us to solve problems in physics, engineering, biology, sociology, and governance all at once, and sustain that solution without failure for longer than most civilizations in recorded human history have managed to remain stable and unified. That is the real distance to the nearest star, not 4.24 light-years on a chart. 4.24 light-years, measured in human consequence, in human patience, in the sheer staggering commitment it would take to actually go there. Step back far enough, and this entire discussion says something quietly important about where we actually live. Earth is not just a planet, among countless others, interchangeable with whatever lies at the end of a future interstellar voyage. As far as every piece of evidence currently available to us suggests, it's the only place in the accessible universe where a person can simply walk outside and breathe unfiltered air, where sunlight isn't filtered through a viewport, and no engineered life support stands between them and survival. Proxima Centauri b might be rock and radiation. It might, against the odds, hold some surprise we haven't anticipated. We won't know for certain until instruments far more capable than anything we currently operate are able to study its atmosphere directly. That may still be decades away, even for remote observation alone. What we do know, right now, without any uncertainty at all, is that Earth already works. It already has breathable air, liquid water, a magnetic field that deflects the same cosmic radiation that would threaten any interstellar traveler, and an atmosphere thick enough to burn up nearly everything that falls toward it from space. Earth already solves every one of the extraordinary engineering challenges described tonight. The shielding, the closed ecological systems, the radiation protection, the multi-generational sustainability. It does all of it quietly, continuously, at planetary scale, entirely for free. That's easy to take for granted, precisely because it requires no effort from any individual person to keep functioning. Weigh that against the actual scale of what it would take to build even a rough, failure-prone approximation of those same conditions aboard a spacecraft bound for another star. Earth starts to look less like a starting point we'll eventually outgrow, and more like an almost impossibly rare and fragile achievement. One that took over 4 billion years of geological and biological history to produce. And one we are still, today, the only known beneficiaries of anywhere in the universe. Let's walk through what an actual mission might look like, start to finish, using the most optimistic, realistic numbers available today, just to make the shape of this journey concrete rather than abstract. Imagine a crewed vessel launches sometime in the next century, powered by an advanced fusion drive reaching roughly 12% of the speed of light. It's similar in principle to the old Project Daedalus design, but scaled up to support a living crew rather than an unmanned probe. At that speed, the outbound leg to Proxima Centauri takes approximately 35 years. Add several more years for deceleration, since slowing from 12% of light speed requires almost as much propulsive effort as the acceleration phase did. Call the full one-way trip 40 years. A crew member who launches at 30 years old would arrive at Proxima Centauri around age 70. If they have children during the voyage, which most mission designs assume as a practical necessity, those children would be raised entirely aboard the ship. They'd reach adulthood only as the mission nears its destination, never having known anything but the interior of that vessel. Meanwhile, back on Earth, only slightly more than 40 years pass for everyone left behind, thanks to the modest time dilation effect, even at 12% light speed. That's roughly 1 extra month of difference, not enough to create the dramatic generational gap you'd see at higher relativistic speeds. But it's still enough that anyone tracking the mission from Earth would need patience measured in decades regardless. A message sent the moment the crew begins. Their approach to Proxima Centauri would take another 4.24 years to reach Earth. That means the people who launched this mission would not know it succeeded until nearly 45 years after departure. An entire working career's worth of waiting for confirmation that the ship they built made it to the other side alive. There's a particular kind of silence at the center of all this, and it has a different shape than ordinary distance. When explorers crossed unknown oceans throughout human history, using nothing more than wind, stars, and accumulated knowledge passed down through generations of navigators, they were isolated too. They were cut off from home for months, or occasionally years at a stretch, uncertain whether they would ever see their families again. It was genuinely dangerous, and it demanded real courage. But even in the worst case, that isolation was measured in months or years, a span a single human life could absorb and recover from. The isolation built into interstellar travel operates on a completely different order of magnitude. It isn't measured against a single lifetime. It's measured against the lifespan of everything a person has ever known: family, culture, language, and in the case of a generation ship, the entire concept of returning home at all, since nobody aboard would live to see it. Their descendants would arrive at a destination none of their ancestors ever actually reached themselves. This is the quiet, uncomfortable truth sitting underneath every optimistic diagram of an interstellar spacecraft. The distance to Proxima Centauri isn't simply a technical obstacle waiting for a clever enough engineer to solve it. It's a fundamental reordering of what it means to leave home. It's stretched so far beyond ordinary human experience that our existing frameworks for talking about journeys, departures, and returns barely apply anymore. We have words for someone who moves to a new country and never goes back. We don't really have words for a population that is born, lives, and will go entirely inside a machine. A machine traveling between 2 points in space that neither they, nor their parents, nor their grandparents will ever both see with their own eyes. And yet, knowing all of this, the question of why anyone would still consider going at all matters just as much as any of the engineering details. Every serious proposal for interstellar travel carries the same underlying motivation. From breakthrough Starshot's tiny gram-scale probes to the fully theoretical generation ship designs studied by groups like Icarus Interstellar. Not the expectation of finding paradise at the other end. Not even, necessarily, the expectation of finding anywhere habitable at all. The motivation is closer to something more fundamental. A refusal to treat the boundary of our solar system as a permanent ceiling on what our species is capable of attempting. There's a long pattern in human history of expansion into environments that offered no guarantee of survival and no promise of comfort, driven forward anyway by curiosity, necessity, or sheer stubbornness. Humans crossed into the Americas across a land bridge during an ice age, with no way of knowing what lay beyond the ice. Pacific Islanders sailed thousands of miles of open ocean in double-hulled canoes, navigating by starlight, wave patterns, and the flight paths of birds. They settled islands separated from each other by distances that, at the time, must have felt as vast and unknowable as interstellar space feels to us now. None of those journeys were guaranteed to succeed. Many of them almost certainly ended in tragedy for those who attempted them and failed. But enough succeeded that entire new branches of human civilization took root in places nobody could have reached by standing still. Interstellar travel, viewed this way, isn't a rejection of how difficult the distance actually is. It's simply the next entry on a very old list of journeys that seemed impossible right up until the moment someone attempted one anyway. Proxima Centauri isn't necessarily even the best long-term target, despite being the closest, and that detail says something important about how we should think about interstellar exploration going forward. Distance is only one variable. Habitability, stellar stability, and scientific value matter just as much when choosing where to actually aim. TRAPPIST-1 is a red dwarf system about 40 light-years away, roughly 10 times farther than Proxima Centauri. It hosts 7 roughly Earth-sized planets, several of them within the star's habitable zone, discovered through careful observation beginning in 2016 and refined extensively since. Some researchers argue that a system like that, despite being far more distant, might ultimately prove a more scientifically valuable destination than Proxima Centauri. It offers multiple potentially habitable worlds to study, rather than a single planet orbiting a star known for violent, atmosphere-stripping flares. This raises an uncomfortable strategic question for any future civilization actually planning an interstellar mission. Do you send your first, most expensive, most carefully engineered attempt to the closest possible target, simply because closest means shortest travel time and lowest risk, even knowing that target might turn out to be scientifically disappointing? Or do you accept a longer, harder, more dangerous journey in exchange for a genuinely better destination? There's no obviously correct answer. It's the kind of decision that would likely consume decades of scientific and political debate long before a single ship ever left the ground. Even choosing where to go turns out to be far more complicated than it first appears. Go back to the time dilation numbers for a moment, because there's a version of this story that sounds almost hopeful until you look closely at what it actually costs. At 99% of the speed of light, a speed still firmly inside the bounds of relativity, even if wildly beyond anything we can currently produce, the time dilation factor becomes roughly 7. That means a crew traveling to Proxima Centauri at that speed would experience the 4.24 light-year journey as lasting only about 7 months of their own subjective time. From the perspective of anyone watching from Earth, the full 4.24 years, plus the years needed to decelerate and accelerate, would still pass exactly as expected. Push the speed even higher, to 99.9% of light speed, and the crews experience time drops to just a couple of months, while decades continue to pass back home. This sounds almost like a loophole, a way to make interstellar distances collapse for the people actually making the trip. In a narrow sense, it is exactly that. But it comes at a cost that scales in the opposite direction just as sharply. The energy required to accelerate any meaningful mass to 99% of the speed of light is almost inconceivably larger than the energy required to reach even 20% of that speed. The relationship between velocity and required energy isn't linear. It curves upward and eventually approaches infinity as you get closer and closer to the speed of light itself. There is no version of known physics, and no remotely foreseeable engineering that gets a crewed spacecraft anywhere near 99% of light speed. Time dilation is real, and it would genuinely shorten the subjective experience of an interstellar crossing for anyone traveling fast enough to benefit from it meaningfully. But the speeds required to actually benefit from it sit so far beyond anything achievable that this particular escape hatch remains permanently closed to us, at least for the kind of technology we can seriously plan around today. There's an important distinction between robotic missions and crewed ones, because almost everything discussed tonight becomes dramatically easier the moment you remove a living crew from the equation. A robotic probe doesn't need life support. It doesn't need food, water, breathable air, or artificial gravity. It doesn't need psychological support systems, social structures capable of surviving centuries, or genetic diversity sufficient to sustain a healthy population. It can be built far smaller and far lighter, which directly reduces the energy required for both acceleration and deceleration. It doesn't need to return, and it doesn't need anyone aboard to feel any sense of purpose or meaning across a multi-generational journey, because there's no one aboard to feel anything at all. This is exactly why every realistic near-term interstellar proposal focuses entirely on robotic exploration rather than crewed missions. From breakthrough starshot to more ambitious follow-on concepts. A swarm of tiny probes, each carrying cameras, spectrometers, and communication equipment, could realistically reach Proxima Centauri within a human lifetime. That's still extremely difficult, but it sits far closer to what we can actually imagine building in the coming decades. Those probes could photograph Proxima Centauri b directly, measure its atmosphere if it has one, and transmit that data back to Earth, arriving just over 4 years later. That's still an extraordinary achievement, arguably one of the most significant in the entire history of space exploration, offering humanity's first direct, close-range look at a planet orbiting another star. It simply isn't the same achievement as sending people. Honestly, these two goals, robotic exploration and human settlement, may end up on completely different timelines. Robotic missions to Proxima Centauri are potentially achievable within this century, while crewed missions may remain centuries away if they ever become achievable at all. There's a strange third option, one that would let us study Proxima Centauri b in incredible detail without ever sending anything there at all. It relies on an effect predicted by general relativity called gravitational lensing. The immense mass of an object, in this case our own Sun, bends and focuses, light passing near it, acting like a naturally occurring lens. Beyond about 547 astronomical units from the Sun sits a region called the solar gravitational lens focal point. There, light from a distant target would be bent and magnified so dramatically that a telescope could theoretically resolve continents, oceans, weather patterns, and possibly even signs of vegetation on a planet light years away. And it could do that using nothing more advanced than instruments we could plausibly build today. The catch, and there's always a catch in this story, is that 547 astronomical units is itself an enormous distance. It's roughly 3 times farther than Voyager 1 has traveled since its launch in 1977, nearly 50 years ago. Even using a relatively fast propulsion concept, reaching that focal point would likely take several decades. And once there, a spacecraft would need to hold an extremely precise position and orientation for the observation to work correctly, correcting continuously for the Sun's own motion and the target star's motion, all from a location roughly 14 times farther from Earth than Pluto. It's a genuinely achievable idea using foreseeable technology, arguably far more achievable than any crewed mission to Proxima Centauri itself. Several research groups, including engineers at NASA's Jet Propulsion Laboratory, have published serious mission concepts exploring exactly this approach. It wouldn't get us there, but it might, within our own lifetimes or those of our children. Let us finally see Proxima Centauri b, clearly enough to know for certain whether there's anything worth the extraordinary difficulty of actually making the trip. Then there's the idea that occupies the far edge of theoretical physics, the concept that shows up constantly in science fiction and almost never in serious engineering proposals, for good reason. Faster than light travel, in the form most people imagine it, using some kind of warp drive or wormhole shortcut, remains firmly in the territory of speculative theoretical physics rather than anything close to an engineering roadmap. The mathematics of general relativity does technically allow for solutions describing a bubble of warped spacetime. In principle, it could carry a ship to a distant destination without the ship itself ever exceeding the local speed of light within that bubble. Physicist Miguel Alcubierre first formally described the idea in 1994. But every known version of that solution requires forms of matter and energy with properties that have never been observed to exist anywhere in the universe. It's sometimes called exotic matter, possessing what's known as negative energy density. No experiment has ever detected it, and many physicists suspect it may not be physically realizable in any usable quantity at all. Wormholes face a similar problem. The equations of general relativity permit their existence mathematically. But keeping one open and stable long enough to pass through would again require exotic matter in quantities and configurations we have no known method of producing. It's genuinely important to be honest about this distinction. These aren't engineering challenges waiting for better materials or bigger budgets, the way antimatter production or fusion propulsion are. They're open questions about whether the underlying physics required even has a physical counterpart anywhere in reality. Until or unless that changes, and there's no current evidence suggesting it will, every serious mission architecture for reaching Proxima Centauri has to work within the conventional limits already described tonight. Slower than light. Bound by the speed of light as an absolute ceiling. Paid for entirely in decades, centuries, energy, and risk, rather than in any shortcut physics has yet to actually provide. Consider, for a moment, how we actually came to know Proxima Centauri exists at all. The story of studying it from a distance is itself a reminder of how much can be learned without ever leaving home, and how much still remains locked away specifically because we can't. Proxima Centauri wasn't discovered until 1915, identified by Scottish astronomer Robert Innes, working at the Union Observatory in South Africa. He used careful photographic measurements to detect its faint light and confirm it was gravitationally bound to the brighter Alpha Centauri pair, despite being invisible to the naked eye. For decades afterward, astronomers slowly refined its distance, its mass, and its temperature, piecing together a portrait of the star, using nothing but the light it happened to send our way. The breakthrough that let us find planets around it came from an extraordinarily precise technique called radial velocity measurement, which detects the tiny gravitational wobble a planet induces in its host star as it orbits. In Proxima's case, that wobble is so small it shifts the star's position by mere inches per second. Detected across light that has already traveled 25 trillion miles before it ever reaches our instruments. The European Southern Observatory's HARPS spectrograph, along with follow-up observations from the Very Large Telescope, gathered years of these measurements before confirming Proxima Centauri B's existence in 2016. Every fact we currently know about that planet, its approximate mass, its orbital distance, its likely exposure to stellar flares, was derived entirely through this kind of painstaking remote analysis. No single photon of direct light from the planet itself has ever been definitively captured and separated from the overwhelming glare of its host star. We have learned an extraordinary amount about a place we have never touched, using nothing but starlight and mathematics. That fact alone says something remarkable about human patience and ingenuity, even as it underscores exactly how far still separates knowing about a place and actually reaching it. Picture, just for a moment, what an actual departure might someday look like if humanity ever does commit to a mission of this scale. Not the launch itself, which would likely resemble any other rocket launch in its opening minutes. Think instead about the years surrounding it. Decades of engineering. Decades of political negotiation between nations or coalitions large enough to fund something this expensive. Decades spent selecting and training a crew who understand, with complete clarity, that they are volunteering for something with no historical precedent. Families would say goodbye, knowing that meaningful reunion becomes essentially impossible, even in the most optimistic mission designs, using relativistic speeds substantial enough to matter. Entire careers would be spent by engineers who will go without ever seeing whether their designs actually worked. Their only reward would be incremental confirmation, sent back across years of communication delay, that each stage of the mission completed successfully so far. There's something almost unbearably patient required by a project like this. That patience has to be built into institutions, into funding structures, into cultural memory itself. Sustained across generations of scientists and engineers and taxpayers who will never personally witness the outcome. Every major human infrastructure project we've ever undertaken required sustained commitment across years or decades. Cathedrals that took centuries to complete. Canals and railways spanning continents. Even long-term scientific endeavors, like the International Space Station. An interstellar mission would require that same kind of sustained institutional patience, but stretched across a span of time longer than most nations currently in existence have themselves existed. It's not obvious that any human institution, as currently structured, has ever proven capable of maintaining unbroken commitment to a single project across that length of time. Building one that might turn out to be a harder problem than the propulsion physics itself. There's one more angle here, and it has to do with what actually counts as success for a project this difficult. Most human endeavors are judged by whether they achieve their stated goal within a reasonable time frame. Whether a bridge gets built on schedule, whether a vaccine reaches approval, whether a spacecraft lands where it was aimed. An interstellar mission breaks that framework completely, because for anyone involved in its early stages, success can never be personally witnessed. The engineers who design the propulsion system will be gone long before the ship arrives. The scientists who select the target planet will never see whether their choice was correct. Even the first generation born aboard a generation ship will go without ever knowing whether their descendants, centuries later, actually reach Proxima Centauri safely. This forces a strange redefinition of purpose. It has more in common with planting a tree whose shade you will never sit in, or laying the foundation of a building whose completion you'll never see, than with any conventional scientific or engineering achievement. Every person involved in the early stages of a real interstellar mission would need to find meaning in contribution rather than completion. In the act of moving the project one step closer to a destination they personally will go without ever reaching. That's an unusual thing to ask of human motivation, and it's fair to wonder whether we're actually capable of it at the scale required. Some evidence suggests we might be. People have devoted entire careers to projects like particle accelerators, decades-long astronomical surveys, and long-term ecological restoration efforts, understanding fully that the most meaningful results might only appear after they're gone. An interstellar mission would simply ask for that same kind of patient, forward-looking commitment, stretched across a much longer horizon than anything attempted before. It would need to be sustained not by one generation of dedicated scientists, but by an unbroken chain of them, passing the project forward like a relay race that spans centuries instead of seconds. Zoom back out one final time to the number we started with. 4.24 light-years. 25 trillion miles. By now, hopefully, that number carries a different weight than it did at the beginning of tonight. It's not simply a distance on a chart, an entry in an astronomy textbook next to the names Sirius and Barnard's star. Measured honestly against the actual capabilities of human engineering, it's a distance that translates into decades of relativistic travel under only the most optimistic near-future propulsion concepts, or centuries of multi-generational transit under anything achievable with foreseeable technology. It's a distance that demands solving problems in physics we've only begun to seriously study. Radiation shielding we haven't yet built at the necessary scale. Closed ecological sustainability we've only tested for a couple of years at a time. Human governance and psychology across timeframes longer than most nations have ever managed to remain stable. And this is the closest star in the entire universe. Not a difficult star. Not a distant, unusually challenging target chosen to make a dramatic point. The single nearest star that exists anywhere, the shortest possible interstellar journey the physics allows for, still demands nearly everything a civilization has to give. That's the real meaning behind the phrase, worse than you think. It isn't that the distance itself is somehow larger than the number 4.24 suggests. It's that the true cost of crossing that distance, measured in energy, engineering, patience, and human endurance, is so much greater than the number alone ever communicates. It's so much greater than most casual conversations about interstellar travel ever bother to explain. Let's return, one more time, to the physics itself, because there's a specific comparison that tends to make the scale of this problem click for people in a way raw numbers alone often don't. Every year, the entire world's civilian and military aviation fleet together burns through roughly 100 billion gallons of jet fuel. That's one of the largest deliberate energy expenditures our species undertakes annually. The total kinetic energy required to accelerate a single, modestly sized crewed spacecraft on the order of 1,000 metric tons to just 10% of the speed of light is staggering. It exceeds the energy contained in that entire year's global jet fuel supply by a significant factor. And that's before accounting for the roughly equal amount of energy needed again during deceleration at the other end. This is why every serious interstellar propulsion concept eventually turns toward nuclear or antimatter reactions rather than any form of chemical combustion. Only reactions that convert a meaningful fraction of mass directly into energy, rather than merely rearranging chemical bonds, can supply anywhere near the energy density required. It's also why cost estimates for real interstellar missions routinely appear in the trillions of dollars or as a percentage of entire national economies sustained over decades, rather than in the billions typically associated with even our most ambitious current spaceflight programs. The gap between what powers our current fleet of rockets and what would be required to cross even the shortest interstellar distance isn't a gap that better rocket engineering closes incrementally. It's a gap that requires an entirely different category of energy source, one we have only barely begun to master in laboratory conditions, let alone harness reliably at the scale a real mission would demand. There's also a quieter, more personal version of this story, because distance like this doesn't just affect engineers and mission planners. It reframes something about how we relate to the night sky itself. Alpha Centauri is the bright point of light, visible from the southern hemisphere, that contains both Proxima and its two brighter companion stars. Human eyes have watched it for thousands of years. The astronomer Ptolemy catalogued it nearly 2,000 years ago. Countless cultures across the southern hemisphere admired it long before anyone understood what a light year even meant. For nearly all of that history, people looked at that point of light with no concept of how far away it actually was, no understanding that traveling there would even be a coherent question to ask. Now, we know the number. 4.24 light-years. And knowing it changes the experience of looking up at least a little. That point of light isn't simply beautiful anymore. It's simultaneously beautiful and almost taunting, close enough to see clearly with your own eyes on a clear night, yet separated from us by a gap so vast that even our fastest machines would need tens of thousands of years to close it at current speeds. The next time you find yourself looking at a star, any star, remember that what looks like proximity in the night sky and what constitutes actual reachability are almost completely unrelated concepts, separated by physics far more stubborn than distance alone would suggest. This particular topic tends to provoke strong reactions, and those reactions usually split in one of two very different directions. Some people find this information deflating, even depressing. It feels like confirmation that humanity is permanently confined to a single solar system, that the dream of a spacefaring civilization spread across multiple star systems is simply a fantasy that better engineering will never fully deliver. That reaction is understandable. It's also, based on everything we've actually covered tonight, not quite the right conclusion to draw. Nothing described here proves interstellar travel is impossible. It proves that interstellar travel is extraordinarily difficult, requiring commitments of energy, time, and sustained civilizational patience that we do not currently possess. But nothing in known physics rules it out entirely. Other people find the same information clarifying rather than deflating, a useful corrective to decades of science fiction that made interstellar travel look casual, quick, and almost incidental to the plot of a larger story. Understanding the true scale of the challenge doesn't have to diminish the ambition. If anything, it can sharpen it. It replaces a vague, unfocused hope that we'll eventually figure out warp drives or wormholes with a much more concrete, achievable roadmap. Robotic probes within a century. A solar gravitational lens telescope within decades. Incremental advances in fusion propulsion, materials science, and closed ecological systems. Each one is individually useful, even outside the context of interstellar travel. Each one is a real, buildable step, rather than a hand wave towards some future breakthrough. Nobody can actually specify. The distance to Proxima Centauri doesn't have to be a wall that ends the conversation. It can be a scale that reorganizes it, forcing every serious proposal to reckon honestly with what the journey actually costs, rather than skipping past that cost toward a comforting but unearned sense of inevitability. Consider, too, how this problem connects to something closer to home, something we're already grappling with here in our own solar system, on a much smaller but still meaningful scale. Mars sits, on average, about 140 million miles from Earth. Even that comparatively modest distance creates communication delays of up to 22 minutes each way, depending on the relative positions of the two planets in their orbits. Missions to Mars already require crews and mission controllers to plan around the impossibility of a real-time conversation. They have to build autonomous decision-making capability directly into spacecraft and rovers, so they don't have to wait for instructions that might arrive 20 minutes too late to matter. A distance of 140 million miles already forces this kind of fundamental rethinking of how humans communicate with and control machines, and eventually crews, operating far from home. It becomes easier to appreciate just how much further that same problem stretches when the distance in question is 25 trillion miles. Instead, every lesson we're currently learning applies here too. Operating with communication delay. Building systems capable of independent decision-making. designing closed life support systems robust enough to function without immediate resupply. All of it is practice for a much larger and much harder version of the same set of problems. It's one that Proxima Centauri and the rest of the interstellar neighborhood will eventually demand we solve in full, if we ever intend to go there at all. There's also a scientific value to studying Proxima Centauri that has nothing to do with ever physically reaching it, because remote observation alone continues to teach us an enormous amount. Every advance in exoplanet detection technology, refined initially to study systems like Proxima Centauri, ripples outward to improve our understanding of thousands of other star systems across the galaxy. The James Webb Space Telescope has already transformed our ability to analyze the atmospheres of other exoplanets by directly measuring the composition of starlight filtered through those atmospheres as the planets pass in front of their stars. It's not specifically designed to study Proxima Centauri b directly, though, due to the overwhelming glare of its parent star at close range. Future instruments are being specifically designed with the direct imaging of small, rocky, potentially habitable planets like Proxima Centauri b as one of their primary scientific goals. That includes proposed observatories like the Habitable Worlds Observatory, currently being studied by NASA for a possible launch sometime in the 2040s. Every one of these advances matters independent of whether humanity ever sends a physical mission to Proxima Centauri. Understanding whether Proxima Centauri b retains an atmosphere despite its star's violent flares would tell us something profound about how common or rare truly habitable worlds might be around the red dwarf stars that make up the majority of stars in our galaxy. It would help calibrate our search for life elsewhere, refine our models of planetary atmospheric loss, and sharpen our understanding of exactly what conditions a planet needs to remain habitable across billions of years. In that sense, the 4.24 light-year gap between us and Proxima Centauri has never stopped us from learning, however difficult it makes physical travel. It has simply redirected where that learning happens, from the deck of a spacecraft to the eyepiece of a telescope. That's a form of exploration that's less dramatic than a crude voyage, but remains genuinely, meaningfully productive right now, using instruments we're already building today. So, where does that leave us? Standing here in the present, looking up at a star system we can see with our own eyes, but cannot meaningfully reach. It leaves us with a roadmap that unfolds across multiple, overlapping timescales, rather than a single dramatic breakthrough. In the coming decades, expect continued refinement of remote observation. Better telescopes. More precise measurements of Proxima Centauri b's atmosphere, if it has one at all. Gradually, we'll answer the question of whether that world is worth the extraordinary difficulty of ever trying to reach in person. In the coming half-century, expect continued progress on robotic interstellar probes, potentially including an early version of the breakthrough starshot concept or something built upon its foundation. That would offer humanity's first direct, close-range data from another star system, even if only as a brief flyby lasting mere hours. Beyond that, the timeline becomes genuinely uncertain. It depends on breakthroughs in fusion propulsion, materials science, and closed ecological engineering. Most unpredictably of all, it depends on whether human civilization ever generates the kind of sustained, multi-generational political and economic will required to fund a crewed mission of this scale. There's no guarantee that will happen. There's no law of physics requiring it. It would represent a choice, freely made, by a civilization deciding that the extraordinary cost of reaching even the nearest star is worth paying. Not because the destination is guaranteed to be worth it, but because the attempt itself represents something important about who we choose to become. That choice hasn't been made yet. It might not be made for centuries. But understanding exactly what that choice would actually require, honestly, without exaggeration or false comfort, is the necessary first step before anyone can make it at all. There's one more concept to consider, because it represents a genuinely different strategy for interstellar exploration than anything discussed so far. One that trades speed and directness for patience on an almost geological scale. Instead of building one spacecraft and sending it to one destination, some researchers have proposed self-replicating probes, sometimes called von Neumann probes, after mathematician John von Neumann. He first described the theoretical concept of a machine capable of building copies of itself using raw materials gathered from its environment. The idea is that a single probe, sent to a nearby star system, could use automated mining and manufacturing systems to build several copies of itself from local asteroids or planetary material. Those copies would then move on to additional star systems, where the process repeats. Run that process forward across enough iterations, and calculations suggest a fleet of self-replicating probes could theoretically explore the entire galaxy within a time frame of a few million years. That's an almost unimaginably long span by human standards, but genuinely brief when measured against the roughly 13.8 billion year age of the universe itself, or even the 4.5 billion year age of our own solar system. This is, in fact, one of the proposed resolutions to the Fermi paradox mentioned earlier. If self-replicating probes are physically achievable, and no civilization anywhere in the galaxy has ever built one, that silence itself becomes a data point. Maybe such technology is far harder to build than the theory implies. Or maybe no civilization has yet existed long enough, or been stable long enough, to commit to a project unfolding across millions of years. For Proxima Centauri specifically, a self-replicating probe program would still face every problem already discussed tonight for that first crucial hop. The propulsion, the shielding, the deceleration. It simply promises that every star system beyond it might eventually get explored automatically, without requiring a fresh, dedicated mission to be planned and funded from Earth for each additional target. Take a closer look at the shielding research currently underway, because this is one area where genuine, measurable progress continues, even if a complete solution remains years away. Some researchers are pursuing active magnetic shielding rather than relying purely on physical mass. Thick layers of water or polyethylene stacked around a crew compartment. The idea is to build a miniature version of Earth's own protective magnetosphere directly around a spacecraft, using superconducting magnets to generate a field strong enough to deflect incoming charged particles before they ever reach the hull. Early prototype testing has demonstrated that scaled-down versions of this concept can meaningfully deflect charged particle radiation in controlled laboratory conditions. This work is happening at facilities in the United Kingdom and at CERN's laboratories in Switzerland. Scaling that concept up to something capable of protecting an entire crewed spacecraft across a decades-long journey remains a substantial engineering challenge. It would require superconducting magnets powerful enough to generate a field extending well beyond the hull, while consuming a manageable amount of the spacecraft's total power budget, and while surviving decades of continuous operation without failure. But unlike antimatter production or exotic matter for warp drives, active magnetic shielding doesn't require any physics beyond what we already understand and can already partially demonstrate. It's a problem of scale and engineering refinement rather than a problem of fundamental physical possibility. That places it, realistically, among the more solvable pieces of the overall interstellar puzzle, even while the puzzle as a whole remains extraordinarily difficult. There's a broader lesson buried inside all of this about how humans tend to misjudge scale when a number gets large enough. And it explains why the phrase, "worse than you think," fits this topic so precisely. Human intuition handles small numbers well. We can feel the difference between 1 mile and 10 miles, between 1 day and 10 days. That intuition breaks down almost completely once numbers grow past a certain size, because our brains simply substitute a vague feeling of bigness for any real understanding of the quantity involved. 1,000, 1,000,000, 1,000,000,000, and 1,000,000,000,000 all start to feel roughly the same, impossibly large. In reality, each one is 1,000 times larger than the last. A difference so enormous that stacking one on top of another barely registers emotionally, even though it represents a staggering leap in actual scale. This is exactly the trap that swallows most casual conversations about interstellar travel. Someone hears 4 light years, and mentally files it under big but doable. The same emotional category as a long international flight or an extended expedition to a remote research station. But 4.24 light years isn't a bigger version of a long flight. It's a quantity that sits so far outside ordinary human experience that comparing it to anything familiar actually distorts understanding rather than clarifying it. 25 trillion miles isn't like driving across a continent many times over. It's a number that requires an entirely separate mental category, one most people have never had reason to build, because nothing in ordinary life ever demands it. Understanding the true difficulty of reaching Proxima Centauri requires deliberately setting aside the intuitive sense that 4 sounds small. Instead, you have to follow the actual arithmetic. The actual energy requirements. The actual multi-generational timeframes that number translates into once you do the math honestly, rather than trusting how the number feels at first glance. This matters beyond just this one topic too. The same intuitive failure shows up constantly across science communication generally, in discussions of geological time, astronomical scale, and the genuine age of the universe. Numbers that are technically stated correctly still get processed by our minds as roughly equivalent to numbers 1,000 times smaller or 1,000 times larger, simply because both categories land in that same vague mental bucket, labeled really big. Recognizing that failure is often the single most useful step toward actually understanding what a number like 4.24 light-years is telling you. It forces you to stop trusting your gut feeling about scale. Instead, you follow the actual chain of consequences all the way through to the end. Propulsion requirements, energy budgets, travel times, generational spans. Exactly the way we've tried to do together tonight. One final piece of context helps put the whole picture in focus, and it concerns the broader neighborhood of stars, close enough that a future civilization might eventually consider them, once and if Proxima Centauri is finally reached. Barnard's star, at just under 6 light-years, is a fast-moving red dwarf. It's notable mainly for having the largest apparent motion across our sky of any star, drifting perceptibly relative to background stars even within a single human lifetime of careful observation. Wolf 359, at roughly 7.9 light-years, and Laland 21185 at roughly 8.3 light-years, are both faint red dwarfs, barely studied compared to their brighter neighbors. Whatever planets they might have remain largely hidden from current detection methods. Sirius, the brightest star visible from Earth, sits at 8.6 light-years. It's part of a binary system, paired with a white dwarf companion, a dense stellar remnant packing roughly the mass of our Sun into a volume no larger than Earth itself. Every one of these systems represents its own version of the exact same problem discussed all night regarding Proxima Centauri, simply scaled up proportionally with distance. Reaching Barnard's star would take roughly 40% longer than reaching Proxima Centauri at any given speed. Reaching Sirius would take roughly twice as long. None of these targets offer some hidden shortcut around the fundamental challenges already covered: the propulsion requirements, the shielding, the closed system sustainability, the multi-generational governance. They simply stack those same requirements on top of a longer baseline distance, making an already extraordinarily difficult problem correspondingly harder with each additional light-year, separating us from the target. This is precisely why Proxima Centauri occupies such a unique position in any serious discussion of interstellar travel. It isn't simply one interesting target among many roughly comparable options. It's the floor, the absolute minimum distance any interstellar mission could ever possibly involve, the one scenario where the challenge is as small as physics allows it to ever be. And even there, at that theoretical floor, everything discussed tonight still applies in full. There's one particularly striking measurement here, because it puts the whole conversation about speed into a single, comparable frame. Voyager 1, still the fastest object humanity has ever launched into deep space, moves at a little over 10 miles per second relative to the Sun. Light moves at about 186,000 miles per second. That means Voyager 1, our proudest, farthest-reaching achievement in nearly 70 years of spaceflight, travels at less than 1/20,000th the speed of light. To close even 10% of that gap, to reach just 1% of light speed, we would need to accelerate a spacecraft to roughly 200 times faster than Voyager 1 currently moves. And that's still an achievement nowhere near sufficient for a practical crewed mission. Using propulsion technology that doesn't yet exist outside of theoretical design studies and small-scale laboratory experiments. That gap, 200 times faster just to reach 1% of the speed required for even an optimistic multi-decade mission, is the honest measure of how far current engineering sits from interstellar capability. It isn't a gap closed by incremental improvement to existing rocket engines. It requires a genuine leap to an entirely different category of propulsion: nuclear, fusion, or antimatter-based. Each of those remains either partially theoretical, extraordinarily expensive, or dependent on materials we cannot yet produce or safely contain at the necessary scale. Every year that passes brings incremental progress on all of these fronts. Better fusion confinement techniques, cheaper access to space, more sophisticated materials science. But incremental progress, measured in years or even decades, still has to somehow bridge a gap measured in orders of magnitude. That's the piece of this story that any honest accounting has to hold on to, alongside all the genuine reasons for patient optimism already discussed tonight. One last comparison ties several of these threads together, because it deals with information rather than matter, and information moves at the fastest speed the universe allows. Right now, if you pointed a radio telescope at Proxima Centauri and it happened to be broadcasting something back at us, the signal you received tonight would have left that star system 4.24 years ago. If, hypothetically, Proxima Centauri b turned out to host some form of intelligent life, and that life sent a deliberate radio message toward Earth today, we wouldn't receive it until sometime in the early 2030s. Any reply we sent back wouldn't arrive at Proxima Centauri until sometime in the late 2030s. An entire back and forth hello, and then a response to that hello, would span roughly 9 years. And that's even though the message itself, encoded as radio waves, travels at the fastest possible speed anything can move through the universe. That's the final, quiet reminder underneath everything discussed tonight. Even in the best possible scenario, where physical travel isn't required at all, where all that's needed is an exchange of information between two civilizations sitting at the two closest possible star systems in the known universe, meaningful conversation still unfolds across nearly a decade per exchange. Distance doesn't just resist ships and crews and generation-spanning voyages. It resists conversation itself, stretching even the simplest possible exchange of words into something measured in years rather than moments. That is, in the end, the true and complete shape of what separates us from the nearest star. Not simply a wall against travel, but a wall against contact of almost any kind, physical or otherwise. A silence built into the very structure of space and time that no amount of cleverness has yet found a way around. Let's bring together everything this journey has actually required, because laying it out in one place makes the total weight of it clearer than any single piece on its own. Reaching Proxima Centauri using anything close to real, known physics means solving a propulsion problem. Current chemical rockets fall short of it by many orders of magnitude, requiring nuclear, fusion, or antimatter reactions we have only barely begun to master, even in laboratory settings. It means solving a shielding problem against both interstellar dust at relativistic speed and decades of unfiltered galactic cosmic radiation, using materials and field technologies that remain largely theoretical today. It means solving a sustainability problem, building a fully closed ecological system capable of running without failure for decades or centuries, when our best current attempts at similar systems here on Earth have struggled to last even a couple of years without serious complications. It means solving a navigation problem, tracking and predicting the motion of a star system that is itself constantly drifting through the galaxy, correcting a trajectory continuously across a journey lasting longer than most human careers. It means solving a social and psychological problem, maintaining functional, stable human communities across multiple generations confined entirely within an enclosed vessel, none of whom chose to be born into the mission that defines their entire life. And it means solving an economic and political problem, sustaining a civilizational commitment of resources and attention across a time frame longer than most nations in history have managed to remain unified and stable. Every one of these challenges is individually difficult. Together, stacked on top of each other, required simultaneously, without a single failure across any of them for the entire duration of the journey. They form the real distance to the nearest star. A distance measured not just in miles or light years, but in the full weight of what it would take for a civilization to actually cross it. And that, in the end, is why the distance to the nearest star deserves to be understood honestly, rather than smoothed over with the comforting shorthand that Proxima Centauri is just 4 light-years away, practically next door. It is next door only in the sense that everything else in the universe is even farther, a technicality of comparison rather than a meaningful description of reachability. The nearest star in the entire universe still demands more from us than almost anything humanity has ever attempted: more energy, more patience, more sustained cooperation across more generations than any project in recorded history. That's not a reason to stop looking up. It's a reason to look up with a clearer, more honest sense of exactly what separates us from the light we're seeing. We are, right now, a single-planet civilization bound tightly to the star we orbit. We're surrounded by a neighborhood of other stars that remain functionally as isolated from us as anywhere else in the galaxy, despite their apparent closeness in the night sky. Proxima Centauri sits there, visible, close enough to feel almost touchable, 4.24 light-years and 25 trillion miles away, patiently unreachable by anything we currently know how to build. Someday, that might change. The engineering problems described tonight are hard, but as far as we currently understand the universe, none of them are physically impossible. Only extraordinarily, humblingly difficult. Whether we ever solve them depends not on some future stroke of genius alone, but on whether we choose, deliberately and patiently, across generations who will never see the outcome themselves, to actually try. Thank you for spending this time with me tonight, exploring exactly what separates us from the nearest star in the universe. If this changed how you think about the night sky, a like or a subscribe helps this channel keep bringing these kinds of honest, close examinations of what's actually out there. And the next time you find a clear night and look toward the southern sky, remember that the light reaching your eyes left its star 4 years before it ever found you, crossing a gap so vast that even our fastest machines would need tens of thousands of years to follow it home. The universe is close enough to see, and still far enough to remind us exactly how small we are, a distance that measures not just miles, but patience. Wherever you're watching from tonight, thank you for taking this journey through the true scale of what separates us from our nearest neighbor among the stars. Thank you for sticking with every number, every wall, and every honest answer along the way. Good night, and thank you for spending it here with us.